Okay, welcome to this video. It's on density curves, normal distribution, and z-scores. Density curves are a special kind of curve that show a distribution, and they're always above the horizontal axis. We don't want them going below the horizontal axis where it's negative. They have an area of exactly 1 underneath the curve, which is also the same as 100%, we could think of it as. And this helps us understand that the area under the curve represents a percent of data values in that range. So if I were to shade between two values and find the area of that shaded area, that would be the percent of data values that fell between the two endpoints on the x-axis of that shading. We're going to look more into that in future lessons. Normal distributions are a special kind of density curve. They are always unimodal, symmetric, and bell-shaped, like this one. And they are always described by the mean and standard deviation. That's really all you need to know to understand a normal curve. The mean tells you where the center of your curve is, so they're in the middle. And the standard deviation tells you how scrunched and stretched your normal curve is. If it's a smaller standard deviation, it's going to be more narrow. And if your standard deviation is larger, it's going to be more spread out and shorter. We use mean, or mu, this Greek symbol, for mean, and sigma for standard deviation. We are also going to see a couple other abbreviations for mean and standard deviation. We will learn when it's appropriate to use which version later. For now, don't worry about it too much. Okay. Next, we're going to talk about z-score. Z-score is a way to standardize scores. We often talk about the example of ACT and SAT scores. They're both trying to measure college readiness, but have very different scale systems. SAT scores are in the thousands, and ACT scores max out at 36. You could also just use them to compare different tests that you may have taken in a similar class, but with a different teacher or a different test. Here is an example of two students who took a similar test, but were in different classes, and the test had a different mean and a different standard deviation. We're going to use the z-score formula to standardize those so that we can best compare who actually did better. Our z-score formula says that we take the estimate or the observation. This is kind of the data value you're given and that you're interested in the problem. In this case, for Katie, the estimate or observation would be 93, and for Lisa, it would be 81. Those were their scores. Then you subtract the mean and divide by the standard deviation. We could also use this notation, x minus mu over sigma. It means the same thing, but is a little shorter to write. So if we plug in those values for Katie into the z-score, we get this calculation. Her test score was 93. That goes in for x, minus the mean of 80, and the z-score of 6.07. Be careful when you're plugging this into your calculator. You want to do one of two things. Either plug in 93 minus 80, and hit enter, and then divide it by 1.06, or you can type it in all together, but use parentheses and do 93 minus 80, parentheses, 93 minus 80, and then divide it by 6.07. If you do it all together and leave out the parentheses, the calculator will think you're just wanting to divide 80 by 6.06, and you'll get a wrong answer. So careful about that. Next, we can do the same thing for Lisa. We plug in her score of 81, subtract the mean of her test by 60, and divide by the standard deviation of 9.4. When we do that, we get a z-score of 2.23. So when we actually come to compare these test scores, even though Katie's score was higher, she got a 93 versus Lisa's 81, it actually turns out that Lisa did better because she took the harder test and had a better score relative to the difficulty of her test. It had a lower average, and a higher standard deviation. So we can see that Lisa actually did better because she had a higher z-score. I will be posting a PDF of these notes, so don't worry if you're missing something. You can find it on the PDF, or you can always pause. Z-scores on a normal curve. Z-scores standardize values so that every normal curve can look the same or similar. They will all have the same center. Z-scores always change the mean of a data set to be 0. So if you take the z-score of a data set and you plug in whatever the mean value is, you will get 0 out. So a z-score on a normal curve will always be at 0. And then we go out 1 standard deviation, 2 standard deviations, and 3 standard deviations. We'll learn more how to use this curve to help us answer problems in the next lesson. We can also solve some other probability or some other questions using z-scores. We can use it not only to find the z-score itself, but also to find for some of the other missing values. So in this case, we want to solve for x. We've been given the z-score, we've been given the mean, and we've been given the standard deviation. So how we're going to do that is we're going to first remember the z-score formula. So the z-score formula tells us z equals x minus mu over sigma. We're going to plug in what we know. 1.3 is our z-score, that goes in for z. X is missing, we'll leave it as x. Minus 12, which is mu, or our mean, over 12, which is the standard deviation. To get rid of 12 in the denominator, our first step is to multiply by 12 on both sides. When we do that, we get 15.6 equals x minus 12. The 12's canceled out. And then to solve for x, we just add 22 to both sides, and we get x equals 37.6. So we were able to find the original data value that has a z-score of 1.3. We could also do this if we wanted to find the standard deviation or the mean. So here's an example finding the standard deviation. We are, again, remember our z-score formula. We plug in what we know, the z-score of 1.3, mu is 4, x is 7, and we get that. I'm using sigma for standard deviation because it's a little faster to write. Then I can simplify the numerator and do 7 minus 4, so I get 1.3 over sigma. Then, in order to get sigma out of the denominator, just like on the last problem, we multiplied by 12 on both sides. I can still do that even if I don't know what sigma is. So I'm going to multiply by sigma on both sides. And now the sigmas will cancel, and I get 1.3 sigma equals 3. And to solve for sigma, I divide by 1.3 and get a z-score, or a standard deviation of 2.31. Standard deviation. Awesome. We are almost done with the video. The last thing we're going to talk about is assessing normality. I've already talked about a couple of times that normality is really important. There's going to be a lot of things that you're going to learn about z-scores and normal distributions that will help you solve a variety of really important problems. And so you need to know if you have a normal data set before you can use some of those tools. And so we want to be able to check and see if a data set is normal. So here is a data set. If you remember how to plug that into your calculator, you can go ahead and pause the video now. If not, I can show you how to do that step and you can pause it in a minute. Okay. If you don't remember how to plug data into your calculator, you turn it on. I'm going to clear out those last calculations. And to enter data, you always hit Stat and then Edit. That's going to let you edit your lists. I had a project that I was working on where I already was using the first 5 lists, so I decided to enter my data into list 6. So here's all my data. You can see it. One tip that I use, the easiest way to make a mistake on anything involving statistics in the calculator, is to misenter your data. You miss a data point, you enter a data point twice. It happens a lot more frequently than you would think. You want to be careful. So what I like to do is if my data is in rows, I can see that the first row has 5 data points. The last data point in that row is 14.5. So as I'm entering data, once I get to that 14.5 at the end of my row, I notice, so here's that 14.5, I see that it says L6 parentheses 5. That means that it's the 5th data point I've entered. Using that can kind of just help me make sure that I haven't missed a data point or double entered one. I just kind of check at the end of every row. So there's another 5 data points in the second row. So by the time I get to 15.2, I should have entered, that should be the 10th data point. So I can scroll down, 15.2, oh, it is the 10th data point. I feel pretty good. You also just want to be careful that you are typing them correctly. It's also easy to miss a decimal point or add a 0 or something like that. So do look over your data when you're done so that you know it looks good. That way you won't have any surprises later on. Once you've entered your data, we want to graph it. There are going to be 2 graphs that are going to help us assess normality: histograms and normal probability plots. Histograms is what we'll do first. So to graph a histogram, I go second, y equals. I can go into my first stat plot, make sure that it's turned on. I made that mistake earlier. I was practicing this problem and forgot to turn it on, and I didn't get anything, and I was confused for a minute. So make sure it's on, make sure it stays highlighted so you know it's on. And then we want to graph a histogram. That is the histogram shaped graph there that we see. Hit enter so it stays highlighted. That way, even when you move your cursor away, it's still highlighted. My data is in L6. If your data was in L1, which it probably is, you can hit second L, and then number 1, above number 1, you see a yellow L1, and it switches it to L1. Obviously, my data isn't there, so I'm going to hit second. I'm going to hit 6 because I see the yellow L6 above it, and change that back. Once I do that, I can hit graph, and I see my data. Now, your data might not look like this. Couple of things that could have happened. It might look really weird, and you could hit zoom and then go down to zoom 9. That's stat. And then my data looks like this, which is close. And this is actually totally correct. I just decided that I wanted to see a little bit better what this bar was, and to see a little bit smaller bars. So how I did that is I went into Window. I scrolled down to X scale. This is telling me how often we're splitting to a new bar, how wide those bars are. So this says that currently it's 0.91. That's almost 1 unit. I want those to be a little smaller because there's some decimals in my data. I'm going to change that to 0.5. And I can hit graph. And now we see that first graph that came up. You don't have to do that, but I think it's valuable to see. So now I look at my data. I see that it looks roughly normal, right? I can see that it starts out low, comes to a peak, and goes down. Now, it kind of has 2 little peaks, but really they're sort of in the same curve. I can see myself sketching out a normal curve above it. I think it's pretty normal, but I want to make sure that those 2 curves aren't an issue. Another type of curve I can look at is the normal probability plot. Oh, by the way, if you were assessing normality as a part of a homework problem, you wouldn't want to just do it on your calculator and then not record it. You'd want to sketch a graph of that or take a screenshot and submit it that way. Do not just say that you looked at it on your calculator. Next, so the normal probability plot, how I do that is I go back to my stat plot, so second y equals, go back into plot 1. It should be on because I just graphed it. And I'm going to change, instead of graphing a histogram, I'm going to keep using my over arrow to graph this last one. It's kind of looks like a scatter plot, but it's all in one line. That is a normal probability plot. And when I hit enter, my options change a little because these are kind of special. My data list is still L6. And then I'm going to leave X highlighted. These are just the markers. Doesn't matter whether you use the circle, the plus, or the dot. I'm just going to leave it on the default circle. And I'm going to hit graph. In a normal probability plot, if your data is normal, it will be a line. So you might want to write that down. If your data is normal, it will be linear. That's really important. And we see that our data is indeed in a pretty solid line. Obviously, it's real data, so it'll never be in a perfect line, but that is about as close to linear as a data set can get. And so we feel pretty confident that this data set is normal. If we saw some curve or some data points that really were outside of that linear model, then we might be concerned that there might be something else going on and this data isn't truly normal. And we would need to think of some other techniques other than the ones we're going to learn in the future sections. All right, that's it for this video. Have a good day.